With Houdini 17.5, Vellum got a new feature. It's easy to overlook, it's just a single checkbox in some constraints, but it can help make your simulation look more realistic, more physically plausible. And what I want to do in this tutorial is quickly show you the feature and then use it for this animation of this cube grid that's held onto some geometry by a bunch of wires which then break. But first let's talk about this new feature, and to show it to you I'll drop down a grid, dive in there and maybe scale back the grid to be 2 by 2, and also drop down a box. Just ghost this and move up the grid so it sits on the top face of the cube here. Next I'll highlight the box and drop down a Vellum configure soft body, a strut soft body that is, to which I'll attach another Vellum constraint. Set this to attach to geometry and wire in the grid in the third slot up here. Also in my box what I want to do is I want to set the primitive type to a polygonal mesh and let it set at a default 4 by 4 by 4. Let's just drop down a Vellum solver here really quickly, and in the solver itself just increase the substeps to 2 and dial back the constraint iterations to say 20. In the attach constraints, the only thing I want to do is dial back the stiffness to a really low value like 5 for example, and then simulate this. So this runs quickly and it bounces there, it just dangles. That's pretty much what we'd expect. So let's just go up one level and copy this whole grid here, paste it, and then translate it a bit to the side so we can compare solver settings. And what I want to do in this simulation here is in the Vellum attach constraints, I want to check stiffness drop-off. That's the new feature I've been talking about, and increase its value to 0.8. And what stiffness falloff does, it takes the stiffness of these constraints that we created here, and checks how far they are from their original position, and multiplies their stiffness by a factor, which is 1 if the constraints are at their original position, and 0 if the constraint reaches this distance from its original position. So the further a constraint stretches out, the less stiff it is, and this simulates a physically plausible behavior in springs, because you cannot stretch out a spring forever. At a certain point it'll lose its stiffness and basically break. So let's highlight the Vellum solver, quickly save this, head up one level, and simulate both cubes here. Let's just toggle real time here and play this. And you can see while this cube keeps bouncing for almost forever, this one here eases into its final position. So this one here looks physically more plausible. Also what we can do is we can very well combine this stiffness drop-off with the actual breaking of the constraints. So we can simulate a rubber band or a spring that's been well stretched past its breaking point, so it releases. So let's do that by building a bit more of an elaborate setup, but again starting out with a grid, which again will scale to 2 by 2 and move it up to 0.5 units. Also I want to increase the rows and columns to say 30 by 30, and then drop down a box. Again, set this box to be a polygonal mesh, it's highlighted, and maybe goes to the grid, and let's check. And later I'd like to create constraints, ropes between the box and this plane here. So let's move down the box a bit, like this, and to be a bit more organic, let's rotate it slightly, that should do it. Also I want to have all my grid points in a group, so let's use a group node, which I'll set to points, call this one fixed, and move all the points in this group. Let's check like this, perfect. Also let's give those two geometries a name, either using the name sop or writing a bit of primitive wrangle code. I'll just use the name sop for now. Let's call the first one piece 1, and the second one piece 2. And then merge both geometries into a single stream. Let's highlight this here and head over to the geo spreadsheet, checking primitives. I've got my two geos called piece 1 and piece 2, and also I've got my point group fixed, so everything is fine. Next I want to generate two groups in this single geo stream, one called soft bodies, that's my grid and my cube here, and one containing the ropes that we'll create. So again, using two group sops, set to primitive, first create a group called soft bodies, I'll put everything coming in this stream into this group. And as I'm going to create a few wires, which I'll call ropes, I want to make sure that this geometry here is not part of the ropes group, which I'll create later. So just make sure by creating another group, this time calling it ropes, and excluding everything from that group. So we have a group called ropes, which has 0 members, and a group called soft bodies, which has all of my primitives in this geostream. Now to create those ropes, I'll use the connect adjacent pieces. wire in my geometry, highlight this, and slowly start increasing my search radius here. Let's just ghost this group here. I don't like this connection here, so yeah, 0.67. So I'm getting those connection lines here. However, one thing that's bad for the following simulation is that these endpoints here are intersecting, are on the same point as the soft body geometry's points here. So we'll have to move those rope endpoints a tiny bit towards the center of each rope. Let's do that using a primitive wrangle. And in here, what I want to do is get the endpoints of each primitive. So I'm going to use a function called primPoints, which will return a list and array of all the points which are part of this primitive. So each rope is a single primitive. This will return the rope's endpoints. As I know that each of my primitives here, each of the ropes only contains 2 points, I can directly access each point's position here, because I know there will be 2 points in this array here. So I'll create a vector, which I'll call pos1. It should be equal to the point's p attribute, and the point is coming in through a 0 input slot, and it will be the first point of this array, so npts 0. Let's just copy this line here, paste it again, call the second position pos2, which will be the p attribute of the second point stored in that array as the point with the ID 1. Next, to move those, I want to get a vector pointing from one point to the other, and I can get that by subtracting the position values from each other. So again, creating a vector, call this diff for difference. It should be pos1 minus pos2. And now I'll take a tiny bit of this vector here and subtract it from position 1 and add it to position 2 to move both points closer to the center of each line. So pos1 minus equals difference times 0.01. Nothing happening because I'm not setting the point's position actually, so I have to do that using the setPointAttrib function because I'm working from a primitive here. I'm running this over primitives, so I cannot just use @p. I want to set the p attribute on our first point, and I want to set it to pos1. So now we're seeing here those points down here will be moved a bit towards the center of each line. Let's just copy these 2 lines here, paste them and modify them slightly. So for position 2, we want to add this value and then write this back to our second point, like so. And now I moved down these points here too, so before and after. So I slightly shrunk those lines. Next, I want to generate some intermediate points for those lines using the resample function, which I'll set to have a uniform sample length of 0.05 units. Now, when I display my primitive numbers, I can see each line is its own primitive. And for what I've planned, I want to change this so that each of those subsegments is an individual primitive. Let's do that using the convert line node. So now each segment is its own primitive. And if you remember my main geometry, I gave my main geometry names, so let's do that here too by just copying down that name sub and calling these ropes here piece 3. So all those ropes have the same name, piece 3. Next, a few groups we need to take care of. The fixed group here. Let's copy this one, paste it down here, and I don't want my points from the ropes to be in that group, so I exclude everything, and then my soft bodies and ropes group, copy those too, wire those in here. And I don't want my ropes to be part of the soft bodies, but I want them to be part of the ropes group, like this. Alright, I think we can merge both streams again. Let's just drag this down so it looks a bit more tidy, and merge both the soft bodies and the ropes. So this is what we have. Now everything that's left is basically setting up the vellum constraints in the vellum solver. So let's do that by first dropping down a vellum configure hair, which I'm going to use for the ropes here. Let's head up here and maybe drag this down. So I want only my ropes group to be a hair. And down here, when I scroll to stretch, I want to set my stiffness to a rather low value of 0.5. Again, this is a value that I found out by trial and error after setting this up. Let's also enable the stiffness drop-off with a value of 0.2. Again, something I found out by trial and error and lots of simulations. Let's call the output group for the constraints hair stretch, and also let's decrease the bend stiffness a bit to 0.01. Later we can dial in the braking and the braking threshold, but I'll leave that unchecked for now. So next let's configure our vellum soft body. And again, I'll take the strut soft body here. and Houdini automatically drops down those two nodes, the cloth and the struts. So let's set up the cloth first. Let's scroll up, and I want to restrict this to the soft bodies group this time. Also, I'll increase the mass a bit, so I have something dragging down on those ropes. And when we scroll down to stretch, this indeed all looks fine. Now for the struts. Again, I want to only affect the soft bodies. I'll check mass and thickness. And again, scrolling down, that all looks fine as is. So next, let's connect the ropes to our grid and cube here by using a vellum constraint again and setting it up to be a glue constraint, affecting only the ropes, and the target should only be the soft bodies like this. So here these little indicators indicate that only at these points and up here I have glue constraints created now. However, these here are a bit wrong, so let's just scroll down a bit and decrease the glue surge distance to 0.02. Maybe for good measure increase the surge points, although it shouldn't make that much of a difference in this case. And that should be it for the glue constraints. Finally, I want to fix those points which are on this grid here, which I can do by heading into the vellum cloth and under pin to animation, select the fixed group here, and that should be it. Now let's drop down our vellum solver. And in here I want to increase my substeps to 3 and decrease my constraint iterations to 12. Let's just save this. Keep our fingers crossed and simulate this. Alright, so far not that different from our previous simulation except those ropes here. Now let's add some braking in those ropes here so they tear, which I'll do in the hair constraint here. Scroll down to the braking tab and select braking, and let's dial in the threshold. And there are several metrics that you could use to determine the stress type that's actually used to break those constraints. I tend to leave this set at stretch stress. You could also use the stretch ratio, but for now, let's just go with stretch stress. And this is really sensitive. This is a really sensitive value. I think I had something like 0.00009. That's 4 zeros after the point. Let's just try and simulate this. Okay, so far no braking, so maybe a bit more sensitive. Yeah, that was way too much. Almost. Getting closer. Yeah, maybe a tiny bit. Yeah, that's what I was looking for. Alright, so that's how I use the stiffness drop-off in conjunction with a few constraints to build this cube or any other object you like that's been held onto some area by those ropes, which then as they stretch, tear. And thanks to the stiffness drop-off, behave physically more plausible. So, until next time, have fun, and it's cheers and goodbye.